Welcome back to ECE 501B. Tonight is homework number 5, assignment is due. Homework number 6, I think that's maybe a week later, that's next Monday. And our second exam is a week from Wednesday. Today I posted some practice material for exam number 2 on the website on D2L. And I also posted the project assignment with a grading rubric, which maybe gives you a little bit more information on how to structure your project and what I'm looking at in terms of how to score points or how to maximize the points that you're getting on that assignment, the project assignment. You might look at the material underneath the course resources module on the content page of D2L. There's our secondary text, which we will get into once we complete the first text, and we aren't going to get through all of the first text, but we'll start skipping around and getting most of it. The first text, which is linear algebra done right. We will then get into how to extend these concepts or ideas into the infinite dimensional setting, or talking about function theory. Oh, I forgot $sign. This is supposed to be the $25 billion eigenvector. I'm sure you didn't realize that eigenvectors were worth that much when you were doing some of these assignments, but if they were tied to Google, which you can, this paper talks about using eigenvectors to rank pages on the web. And they actually, that paper is a nice way of working your way through a technical paper or journal and answering and addressing particular questions, and they sort of walk you through that process. It essentially guides you through the paper by queuing up particular questions as you progress through that paper. That's sort of a nice paper to read, maybe just very quickly to give you a feel for how you could possibly structure your own project based on another paper or a topic that you might be more interested in than eigenvectors or the Google PageRank concept. There's one on football ranking, which was created under the Bowl Championship Series. How do you rank 120 teams when they obviously don't play each other head-to-head, but they might play similar teams? And I scratched out the BCS in 2014. That went away, but the idea is still there. If you're trying to now rank performance or ability of certain teams or other entities, you could maybe use this process discussed in the football ranking. Principal component analysis might be a way to extract useful information from just a given data set. Can you now figure out maybe how this data is aligned? What's the principal direction of that data? If you now just do a scatter plot in multi-dimensions, what is the principal component? That's more of a tutorial type paper. And then there is the road to reality, the general laws of the universe, three of the first 4 chapters of that as a resource. The book is, I don't remember, but it's many hundreds pages long, the whole book. This is just an extract from that. Roger Penrose is a mathematician who is responsible for this Penrose inverse, or somebody was asking about this pseudo-inverse. He is responsible for that concept, and he is a well-read author. He's written more than just this book, and he's pretty good at trying to communicate higher level ideas or concepts to a more broad-based audience. And here he's talking about in chapters 2, 3, and 4. I don't quite remember, but he starts basically with the numbers, the number system. The counting numbers, the natural numbers, the real numbers, the complex numbers, and then he progresses on into additional topics in chapters 2, 3, and 4. It gives you a sample of what to expect in the subsequent chapters in that particular book. That's just some resources that you can use to give yourself some ideas, or you can dig into any of those papers if you so desire. Today what I want to do is get into some more fun stuff. Now we have, yeah, you're giving me the eagle eye with the fun stuff, but now we have inner products. And we can do a lot with that. Now we can talk about orthogonal projection. We just introduced that last time. We'll quickly recap that. Then we will see how we can do a direct sum decomposition of a vector space using this orthogonal projection idea. We'll talk quickly about some properties of the projection operator. We will then be able to get into minimization problems. How can we take a vector in some vector space, and maybe we only are able to model a piece of that vector in another subspace? How do we sort of project or find the best fit in our working subspace from this entire vector space of capital V, for example? We will then talk about linear functionals, which is just a specific kind of linear map, and that's why it's given a name, linear functionals. We're now taking a vector of multi-dimensions and mapping it to the scalars. So anytime you take some vector that may have more than one, or it could have one coordinate, and map it into the scalar, and it exhibits our linearity properties of additivity and homogeneity, then we have this linear functional. We will then talk about adjoints, and we have to introduce a new symbol, so it's T-dagger. It's now superscripted with a dagger, and that's not the same notation as the textbook. I think the textbook maybe uses asterisk, which we've been using for complex conjugate. But here is a dagger, and what in the world, what's an adjoint? You might think about if we now had a linear map in one of the slots, or operating on a vector in one of the slots of our inner product, the adjoint allows us to move that linear map to the other slot and preserve the same numerical value from that inner product. That's what an adjoint is. So that's one way of sort of thinking about an adjoint in terms of a map. Here is our recap from before on orthogonal projection. And now you could start out as a subset. Typically we will make it a subspace, and I hope you remember the difference between those. A subset you could just think of, oh, those are maybe the natural numbers on the x-axis. That could be a subset in two-dimensional space. The subspace might be the x-axis. That subset in a vector space V, then we can define basically the perpendicular subspace to that subset or subspace U. And the perpendicular subspace we call U perp. And that's just now with this orthogonal superscript, U perp, and that's the set of vectors V in our global vector space, capital V, that are orthogonal to all the vectors in our subspace or subset U, either subset or subspace. But whether U is a subset or a subspace, U perp is a subspace. It contains the unit vector, and it has this closure, additive closure element to it. All the vectors, so that's our Las Vegas concept. If you start in U perp, you stay in U perp. If you are doing a scaling or an addition within vectors in U perp. U perp is a subspace. Then we had I think one of the latter results that we finished on last time was Theorem 629. This is from the second edition of the textbook. If U is a subspace, then we can actually create this direct sum decomposition of our total vector space by combining, in this direct sum decomposition sense, a component of our vector in U and another component of our vector in U perp. And we can then create any vector in our vector space V by this unique combination from U and U perp. That's where we want to pick up from today. Let's then start by saying, in the case where we're starting U is indeed a subspace, the direct sum representation of the total vector space V implies there is a unique decomposition of all vectors in V in terms of elements in these orthogonal subspaces, U and U perp. Given some generic vector little v in the vector space capital V, then we can write that vector little v as a sum of two components, U and W, where U is in the subspace capital U and W is the component of W that's in U perp. So we can split this, any vector, all vectors in capital V, into these two pieces. One vector that lives in U and another vector that lives in U perp. And we're going to use this to actually allow us to define a projection. You give me a V, a little v, I'm going to find, let's say, the U that maybe minimizes the norm between V and U. And that will be sort of our, well, let's just talk about projection first, and then we'll get into a minimization problem. This feature of being able to decompose a vector into two pieces that are orthogonal or living in orthogonal subspaces, we use this feature to define a projection. Actually, I should say a projection operator. And we will call that projection operator capital P sub capital U, where this is now the orthogonal projection of V, any vector in our vector space capital V, onto our subspace U. That's what we mean by capital P sub U. And we can state that, we can say that for all vectors in our vector space V, where we can now think of V as U plus W, the component U is living in the subspace capital U, and the component W is living in U perp. We will define P sub U of V. So now if we apply this projection operator onto any vector V, that's going to give us U. Where we've already decomposed V as U plus W, we're just going to take the U piece, where U is living in the subspace capital U. With that definition of a projection operator, it has the following properties. First is this projection operator is in fact a linear operator. I'm sorry. Yeah, a linear operator. I was thinking I said linear map. It's more than a linear map. It's a linear operator. It's taking from a vector space V and going into the same dimension of capital V. But we also know that the range of this projection operator is all of the subspace U. We know that the null space, well, what do we know about the null space of the projection operator U? Can we define that, or is that equal to something? It's U perp, isn't it? Everything that's not in, or that's orthogonal to U, because we know that this projection operator, if it takes a vector and maps it to the zero vector, then that vector must have been in U perp by definition of the projection operator. Maybe re-expressing that, we can say V minus P sub U of V. You could think of this as just being some vector W. Is vector W the way that we've defined it, and where does that live? Or what's that an element of? An element of U perp. And that's true for all vectors V in our vector space. So we take the vector V, we subtract off the projection operator on V from V, and that gives us then something that's in the orthogonal subspace to U, or it's in U perp. What if we now take the orthogonal projection, or the projection operator, and repeat it? So now we take a vector and we project it onto our subspace U. Now we take that same projection operator and operate on that result. Same as the original projection operator, isn't it? We're not changing anything by repeating that projection operation. And we can then think about the norm of projecting onto our subspace U a component of V. How is that norm related to the norm of V? Now just think in terms of a two-dimensional plane. And let's say that you have a vector v that's 1, 1 in xy, and maybe u is the x-axis. It's less than or equal, isn't it? That hypotenuse is less, or it's bigger than, let's say, the horizontal component. So this is now less than or equal to the norm of v, and that's true for all v in our subspace, or in our vector space, capital V. Now we can get to something that's sort of nice. We can actually figure out how to compute that projection operator. And we'll simply use our result from earlier. Meaning, suppose that we have now a basis, an orthonormal basis on our subspace U. Let's say if E1, E sub 2, up to E sub M, Michigan, is an orthonormal basis on the subspace U. Then we can actually write the vector that results from applying this projection operator to any vector v in the vector space that U is a subspace of. If we now said, okay, what's the projection operator P sub U applied to v, how can I write that as a, let's say, a linear combination? We know that where does this live? Where does the vector live that results from projecting this projection operator onto the subspace U from V? It lives in U, doesn't it? In the subspace U. And we already now have an orthonormal basis on U, which means we can write any vector in U in terms of that set of orthonormal basis vectors. And we can find the component of V in the direction of E1 by forming the inner product. And that's now a scalar, and that's going to scale the orthonormal direction E sub 1. And we can also take the component of V in the direction of E sub 2. That also is a scalar, and that's going to now scale E sub 2. And we can keep doing that until we run out of basis vectors. So we take now and project or find the component of V in the direction of E sub M and use that to weight E sub M. And that actually is expression 35 in chapter 6 in the second edition. Which, if you need to then find this result of applying the projection operator onto the subspace U for any vector V, what's that going to require? Suppose you know the subspace U. How do you create this equation 35? If somebody just gives you a vector space V and a subspace U, how do you go about finding this or computing this formula? First, you have to form a basis. And that basis has to be orthonormal, doesn't it? So you first find a basis, then you orthonormalize that with the Gram-Schmidt procedure to get these E's. Once you have an orthonormal basis, then you start forming these inner products, depending on how many basis vectors you have, how long your list is, that's a basis for capital U, you form that many inner products and then use those resulting scalars to scale those orthonormal basis vectors. And then you have a vector little u in the subspace capital U that's projected from V. And it's an orthogonal projection. Because it's now what? If you subtracted this vector from V, V minus this vector would be in U perp. All right, so let's now use those concepts to allow us to basically form or solve minimization problems. Here we're going to say we often run into problems that can be cast or stated in the following form. We might be given U, this subspace in our overall vector space V. U is a subspace of the overall vector space, and now maybe somebody gives us a generic element or vector in our vector space V. And now the problem is, once you've been given this, they might say find a vector in the subspace, find a U in capital U such that the norm of V minus U is minimized. Or find U that is closest to V with U belonging to or living in the subspace U. That's what we're meaning by minimizing the distance or the norm between the vector U and the vector V. And the orthogonal projection actually gives us what we need. The orthogonal projection gives us the tool, or gives us just the tool to solve the above problem. And that's really stated in a proposition, and if you're just half asleep when you're reading this proposition, you may not feel the significance of that proposition. I know that you wouldn't fall into that category. These propositions and theorems and corollaries, they just jump off the page and get you all excited. So, Proposition 36 in Chapter 6 says, if U is a subspace of our vector space V, and we are given an element in our original vector space, or V is an element of capital V, then the norm of v minus p sub u of v is going to be less than or equal to the norm of v minus u for all u in capital U. So if you were just stumbling around in this subspace capital U and picking little u's and comparing the norm of v minus that stumbled upon u to v minus projection operator of u on v, you know that the norm of v minus that stumbled on u is going to be bigger than the norm of v minus the projection operator on v, because that one's going in the orthogonal direction. And if we want equality, in that inequality, then the little vector u on the right needs to be the result of that projection operator capital U on v. U is equal to p sub capital U of v. Let's see if we can justify that via a proof. This is true for all little u, all vectors in the subspace U, so let's just take one of those. Let's say for a given u, then we can write the following relationship. We can say v minus p subscript capital U v, that's the projection operator, and let's look at the square of that norm. The norm is a positive number, we'll just square it. That's now less than or equal to v minus p sub u v squared I hope that you can see where that's okay. But now let's add on to that a term that we know is non-negative. And that term is now p sub capital U of v minus u squared. Where that right-hand term, if we actually took little u on the far right to be equal to the result of projecting v through that projection operator, then that term would be 0. But we're saying for any u in our subspace U. So that term on the far right is greater than or equal to 0. Definition of our norms. Now,
left-hand side and the first expression of right-hand side.
Yes, so the question was, I'm a little bit confused here. You've got the left-hand side is v minus projection operator on v, that norm squared, and now you have less than or equal to the same thing. Something. So now it's sort of like, this seems like a trivial expression. But we are trying to derive this result. Haven't yet gotten there. We want to find the norm, or rewrite that right-hand side as the norm of v minus u. So we're starting with well-known relationships. So this left is equal to the right. I think you are less than or equal to what's on the right. I think you buy that, right? Now what I want you to think about, though, is to think about this as being an A, and this as being a B. And now now I have a vector A, and I'm taking the square of its norm, plus I have a vector B, and I'm squaring its norm. You know that that is equal to, by the Pythagorean theorem, the norm, because, oh, shoot, I'm getting ahead of myself. Sorry. Where does this vector live? v minus p sub uv. So we have, it lives in capital V, doesn't it? But we've now direct sum decomposed capital V into U subspace and U perp. Now it would be nice if these two terms in these right-hand side norms squared were actually in those orthogonal subspaces. And you're now telling me that this is in U perp. Is that true? That's by definition of that projection operator. Where is this piece? Where is P sub U of V? That's in capital U. That's in the subspace U. And where is little u? That was given to be in the subspace U. And if it's a subspace, we know that additivity will keep us in that subspace. So this vector B is in U. So that now we have a vector, two vectors that are orthogonal to one another. Now we can use the Pythagorean theorem. So that we now know that a squared, which is what we're saying, plus b squared is equal to c squared, which is just a squared plus b squared. And what is that clear? So now what do we want? Now we want this. So it's equal to, but I'm going to preserve this less than or equal to because that's what I'm comparing with, is what's on the left-hand side ultimately. But now if I looked at C, which is A plus B, what does that look like? Well, that's now V minus P sub U V plus P sub U V minus U. And that's C squared. That's this piece. And this rewriting of the right-hand side is just the Pythagorean theorem. That's how I've been able to go from the top line to the second line, or the second row in that expression. But now what do I have inside that norm? I now have P sub UV minus P sub UV. Those cancel, and I'm left now with the desired result. That's less than or equal to the norm of V minus U squared. The squares, well, those quantities on the left and right are positive. I can take the square root and end up with my answer. If you wanted a way of sort of interpreting this visually, or a geometric interpretation, it's what we've been sketching a fair amount. Let's say that this is now our subspace U, and maybe now somebody gives us V. That's not in U, it's in our maybe two-dimensional plane, but now we can project this, whoops, to where that's an orthogonal. This is now in U perp, and this point right there is really what we're calling P sub U of V. That's the projection of V, the orthogonal projection of V onto U. And in fact, this is now the closest point in U to that vector V. If you slide that point anywhere on U, you can see that the distance of that dashed line is just going to get bigger or longer. So there's a geometric way of visualizing this, and that's in a two-dimensional plane, but that can be extended to multi-dimensionals. But we maybe can't visualize this in 6 dimensions, but we can abstract it up to those dimensions from this picture. And we have the tools to now do this. Meaning, so the solution of general minimization problem is to take U equal to P sub U of V, where that's really just the orthogonal projection of the original vector V onto U, where U is actually a subspace of the vector space V. And we can really rewrite equation 635 now. But earlier we saw if we had an orthonormal basis on our subspace U, then we know a way to write that orthogonal projection from V onto U. But earlier we saw if we had an orthonormal basis on our subspace U, for example, E1, E2, up to E sub m, then we could have equation 35 saying that P sub U of V is now V. What's the correlation or the alignment of V with E1? Let that scale E1. How is V aligned with the orthonormal basis E2? Use that to weight E sub 2, etc., down to V and E sub m, inner product weighting E sub m. And that's the strategy that I had tried to say. Let me just write that down formally. Our strategy then is that the solution comes down to finding an orthonormal basis on U, and maybe we just have a basis, but you now know how to orthonormalize that with the Graham-Schmidt procedure. The solution comes down to finding an orthonormal basis on U, and then computing inner products. And this is from the second edition, but you can find a similar example in the third edition. In the textbook by Axler, there's actually has a great example of computing this. Axler has a great example involving finding polynomial approximation to the sine of x. It may take place in a function space, but it's still understandable. So that's sort of preparing us for the next textbook. This is now a way to extend these concepts from the finite dimensional setting to function space, but very let's say, standable. And it's understandable because of what we now can visualize or think about in this finite dimensional setting. So there's our minimization problems. That didn't take us very long. Once we had the machinery, now we can perform minimization problems just knowing that we can perform these orthogonal projections onto a subspace, which is maybe where we have to live for our vectors. Let's now go to a new topic. And it's now called, and it's really not a new topic, it's just a more specific or specialized subject or focusing on a particular linear map. Here, linear functionals. A linear functional on our vector space V is a linear map between our underlying vector space V and our scalar field, be the reals or the complex. Which means if we pick a vector, let's say W in our vector space V, then if we form the inner product of any vector V in our vector space with W, that indeed is a linear functional on our vector space V. So you take an arbitrary vector W, and let's say you now just fix that. Now you've created a linear functional. Now you can take any other vector in capital V, put it into our inner product, and inner product does what? It takes two vectors and generates a scalar. And that's what we want for a linear functional. We want to take, and now this linear functional is taking, W is fixed. Now V is our vector from our vector space. It takes a vector from our vector space, little v, and maps to the scalars. So if we just pick a fixed W, now we've created a linear functional. And we've seen this as we already saw that this inner product was a linear map. We already saw it was a linear map. To the scalars. We just hadn't called it this new term, linear functional. We just didn't have a special name for it. Now, it's actually a pretty powerful little concept. What's surprising is that for any linear functional, and now we're going to introduce a new notation. We'll introduce this phi. That's now a linear functional on V. It takes any vector little v in capital V and produces a scalar. That's what we're calling phi. We can pick a vector W in V such that no matter what the linear functional is, if we apply that linear functional, and here's our notation, we're going to apply that linear functional to a vector V, we can now pick a special W, a unique W, such that that linear functional, the answer, or the number that that generates, is going to be equal to V inner product with this special W. That's the special W that we're picking. And that we can just rewrite, or we will rewrite, as a theorem. Theorem 45 in Chapter 6. And that states that given a linear phi, a linear functional, on our vector space V, then there is a unique vector W also in our vector space V, such that the linear vector applied to some vector U, I'm using U and V and W in all sorts of different ways, hopefully it's not too confusing, that will be equal to U inner product with W for all U in V. So you give me a linear functional, and what's a linear functional? What's the description of a linear functional? I'll give you a vector space V, and now you can create a linear functional by what? Taking any vector little v and producing a scalar from that. So you could say, oh, I'm going to just add up all the components in that vector. And that would be a scalar. And that would be a linear functional, just to give you something to sort of think about. Let's now prove this, and the proof will actually result in finding that special W, that nice W. So now you're saying, well, okay, I've given you a linear functional. I would like to be able to find this W so that I could just form an inner product, because maybe I don't want to number crunch. This linear functional might be some really weird relation on those components of the vector space V. So let's look at the proof of this. First, E1, E2, E sub m. Well, no, for some reason I've gone from Michigan to Nevada. This now, let's say this is E sub n. Why is that Nevada? Because I want this to be something on capital V and not on U. U was a subspace of V. So now I'm going to go up to Nevada. And what are E1 through En? It's an orthonormal basis. So let this list of vectors be an orthonormal basis on V. Then I'm going to sort of emphasize the notation. You give me a vector U in capital V. This is now what I'm saying is the linear functional on that vector U. But we've already said that we're using the notation phi sub U. So that's just trying to define or keep us all on the same page. But what do we know about the vector U if it lives in V relative to this orthonormal basis? If I give you a vector U and an orthonormal basis on, let's say, it's a basis, so it spans and it's orthonormal, it's normalized, and that's on V, and now I give you a vector U on V, how can you relate U to this orthonormal basis? It's a linear combination of those orthonormal basis vectors, isn't it? And you know how it's decomposed. You can find a component of U in the direction of E1 through the inner product. And that will be a scalar that we will use to scale E1. You know the component of U in the direction of E2 by the inner product. Use that scalar to scale E sub 2. That's what I'm now going to write for U in those square brackets. The decomposition of U in terms of these basis vectors on V. So let me write this as the inner product of U with E1, E1, plus the inner product of U with E2, E2, and let me keep going until I run out and say U with E sub n, E sub n. This is just the vector U, and this is really just an orthonormal decomposition of U on capital V. Now, what are these pieces in terms of a mathematical concept? Or are they vectors? They're scalars, aren't they? So these are scalars. And they are sitting inside the argument of a linear function. So if phi is a linear function, what do we know about that? We can now slide those scalars outside and have phi operating on E1, have phi operating on E2. That clear? So now the linearity of the functional allows us to rewrite this as UE1 phi E1 plus UE sub 2 phi E sub 2 all the way down to UE sub n phi E sub n. So I'm able to do this because of the linearity property of phi, or the functional. So now I have these inner products scaled by these phis, but what are these phis? If I take an E1 is just a vector in V, isn't it? And now I'm passing that through this functional. So what is phi sub E1, or phi on E1? It's a scalar. So now I have a scalar scaling an inner product, and I have n of those. These are now scalars. And what am I trying to do? Remember what I'm trying to do. I'm trying to show that phi sub u is some inner product of u with something else in the second slot. I now want to put now I have magically, not much magic there at all, but I now have isolated u in the first slot. Now I need to put everything else in the second slot, and I'll have my w. Now, how do I put these scalars into the second slot? I have to conjugate those, and then they just, by the conjugate homogeneity property, they slide right into the second slot. And then I will do what? I'll combine all of those by the additivity of the second slot. And then I will have my vector w in the second slot. So let's write those steps down. By the conjugate homogeneity of the second slot, I can now rewrite this as u phi sub E1 star E1 plus u phi sub E2 star E sub 2 plus, and I just keep doing that for all of these. I have u phi E sub n star E sub n. This step in the verification proof, or in the proof, is now the conjugate homogeneity of the second slot, since those were all just scalars sitting outside those inner products. And now I can use the additivity of the second slot to collapse all of these inner products into one. I can now write this as u inner product with phi sub E1 conjugate E1 plus phi sub E2 conjugate E2 phi sub E sub n conjugate E sub n. This is now just the additivity of the second slot. So that now all of this is really just my vector W. That's a linear combination of my orthonormal basis vectors. I can now say, so phi sub u is now equal to uw. And if you need W, now you can just find W by saying with W equal to, take the linear functional and map E1 through it. Then conjugate that and use that to scale E1. Take the second orthonormal basis vector and apply the linear functional to it, generating a scalar. Take the complex conjugate of that scalar and use that to scale E sub 2. And we just keep doing that. And are we done? Whoops. We found W, haven't we? Now this silly theorem says it's unique. So we aren't quite done. We need to show that it's a unique vector, W. That if you find a W, so if all 20 of you find a W 20 different ways, they better be the same W. So let's see if that's true. We've now shown that the existence of a W is there. We can compute it, actually, with this process. Thus, a vector W exists Is it unique? So now to show this, let's just assume that we found two W's. So now the class has found a W two different ways. Assume that phi sub u is u w1. Somebody has a w1 and somebody else has a w2, but they're both giving us phi sub u. And this is true for all vectors u that we can find in our vector space V. Well, if that's the case, then those are just scalars. Can't we just subtract them if they're equal to each other and get zero, the zero vector or the zero scalar? So we can now say that, 0 is equal to uw1 minus uw2. And that's true for all u. We're almost there, aren't we? We can now use additivity of the second slot. So that now we have u is equal to, 0 is equal to the inner product of u with w1 minus w2. Again, that's true for all u. Well, that's true for all u. Let's pick a specific u. Suppose the u that we want to look at is w1 minus w2. Therefore, consider a particular u where that u is now w1 minus w2. If that's the case, then we have w1 minus w2. That's our u, inner product with w1 minus w2. And from above, that's equal to 0. Now what do we do? Is there a property that we can now impose to show that w1 is equal to w2? the positivity or the definiteness of our inner product. Our definiteness property of the inner product says that the only way that the inner product of A with itself is equal to 0 is an if and only if that vector is 0. Therefore, we know that the vector W1 minus W2 is equal to 0, which says that W1 is equal to W2. Therefore, W is unique. And now we are finished.
But we have considered a particular u equal to
So we know that this is true for all u. So now we can make it true for a particular u. And all we have to show is that these particular, wherever I started, W1 and W2 are equal. And for this particular case, we can show that. So, and we now just had to start with W1 and W2. If you give me a W1 and somebody gives me a W2 and they say they satisfy this linear functional on u for all u, then we can actually show that in fact those are equal. So now we want to pick a particular u. It's true for all u. So now we can pick a particular u to make our case, to make our argument, what we're saying. So that's this notion of linear functionals, what we can do with that. Let's now move on to another topic, which is the adjoint. And for talking about this adjoint, now we need to sort of expand our picture. We actually need two different inner product spaces. If, let's say we have a linear map T that's mapping between V and W. What I'm saying is we need V to be an inner product space. For any vectors little v and capital V, and we need an inner product space because V and W are not necessarily the same. So we need an inner product space for W, where now this V and W are both finite dimensional inner product spaces over the same scalar field F. So if we have a linear map T, then T dagger and again I said that Axler actually uses an asterisk for his, then T dagger or the adjoint that is a map in the other direction. It's a map from W to V defined by I'm not going to have time, I guess, to complete this unless you give me a few more minutes. So now it's defined by, first we pick a W in our codomain in the linear map T, and if we are given phi on V such that phi sub V, so now phi is a linear functional and it's operating on a vector V, that's going to be T sub V of W. And these two vectors here are vectors in W. Then T dagger W is the vector in V such that phi sub V is actually equal to V inner product with T dagger W. And these are vectors in V, which is really implying that T and T dagger are defined, as I said, to sort of move this linear map between the two different slots. T and T dagger are defined such that TVW is equal to VT dagger W. The inner products are on two different inner product spaces, but their result are scalars and they're equal to each other. And if you look at that, you're basically saying, oh, take the linear map from the first slot, and what would be the equivalent linear map to move that same result to the second slot? And that's what we're calling the adjoint operator. I'm sorry, adjoint. It's not an operator yet, unless we specialize V and W to be of the same or be the same. So we'll pick up with adjoints next time. Thank you for giving me those extra minutes.